Here is Team 5's proposal for optimizing a hydroelectric storage system.
The abstract. For Project 2, we were asked by our client to optimize the hydroelectricity storage system while considering various factors. These included overall efficiency, cost of the system, and the system's feasibility. The factors mentioned earlier were some of the determining aspects of our model design. The overall efficiency was one of the outputs for our project. The cost was determined based on the resources and amount of resources used. The system's feasibility was determined by looking at a mixture of the two previous factors. Introduction. Our main goal was to create a model that can be used to help optimize the pumped hydro storage facility design. Solar energy that is not immediately used goes to waste. A pumped hydro storage system is able to take unused energy from a solar field and convert it to hydroelectricity as well as store it. This method is an effective way to store clean energy. Next up is project management. We had different roles for this project. Some of these included a recorder, a coder, a meeting coordinator and timekeeper, an encourager/gatekeeper, as well as a devil's advocate. Whereas multiple people worked on the model simultaneously. The top picture in the project management section of the slide is the top part of the work breakdown structure, showing our initial concept of the general categories and tasks associated with each goal. The bottom picture in the project management section is our Gantt chart. The first third of the work period was spent researching and brainstorming for the project. A little bit of modeling was also done during this period. The second third was spent working on the model and calculations. The final third was reserved for the presentation and final report. Documentation and reporting was completed throughout the work period.
The initial step in designing the hydro storage system was choosing the appropriate zone. Before a decision was made for the zone, the team conducted an analysis of each of the zones by identifying any potential environmental and cultural concerns, preparation and construction costs, and by calculating the areas and perimeters for each zone. The team then made a decision matrix, as shown in the top right-hand corner in the methods section, in order to effectively decide which zone would be the most ideal to construct the system on. The decision matrix considered factors such as the cost of initial research, the cost of the access road, the cost of site preparation, the potential energy the reservoir would have in each zone, and cultural and environmental concerns, with cultural concerns having the most weight. After a thorough analysis of these factors, the team ultimately decided on Zone 3. The next design decision to be made was the number of pipes to be utilized. The options were narrowed down to one pipe for both draining and filling, and two of the same pipes, with each being used for either one of these functions. Another decision matrix was made to make this decision with cost, efficiency, and how well each design would perform its intended function. The team then chose to utilize two pipes for the system. Another decision matrix was made to determine the necessary height for the reservoir wall. Each possible height was considered, along with the amount of mass each wall could store, their corresponding potential energy, and the cost. The team decided to make the wall 20 meters high due to its ability to store the most potential energy. For the pipe bends, the team also decided to include two 45-degree bends after a thorough geometric analysis of the site. The first bend would be at the base of the hill, near the turbine, and the second bend would be at the top of the hill, about 26.8 meters from the base of the reservoir. The pipe installations would be raised as well in order to ensure that the pipes would reach the base of the reservoir. Finally, the pipe diameter for the system was determined to be 1.5 meters for each pipe. The diameter was determined by finding the median of the available pipe diameters, as it would have a moderate cost and would limit any additional energy losses from higher velocities.
When deciding factors that could be within a range of values, such as velocities, volumetric flow rates, pipe frictions, turbine efficiencies, and pump efficiencies, we used code to determine the possibilities and the best outcome. The first code took possible flow rates and calculated the velocity and time to drain or fill. For pumping water, we narrowed down our velocities to being from 25 meters per second to 45 meters per second, and the time to fill below 6 hours because we wanted the water to be pumped quickly and use any available solar energy as quickly as possible. The possible flow rates going up were any number between 45 and 79, and resulted in time to fill being between 4.91 hours and 2.8 hours. For draining water, the code followed the same steps, but the time had to be below 12 hours, and we wanted the velocity between 10 and 16 meters per second. The reservoir had to be able to drain in under 12 hours. This resulted in flow rate values between 19 and 28. In the bottom left corner of the method section, you can see some of these flow rates with their corresponding velocities and times. After running the first code, we had a set of possible velocities and flow rates for both pumping and draining water. The second code took those sets and combined them with possible turbine or pump efficiencies and Darcy friction factors. Every combination went through the code and the best combination was returned. For draining water, the energy losses from pipe bends, friction within pipes, and turbine efficiency were subtracted from the energy in the reservoir to find the final energy. The code then calculated the cost of this particular combination. The code went through all of these combinations and remembered the combination with the highest ratio of final energy to cost. This section of the code is shown in the bottom right corner of the method section. This way, the results would give us the best energy output for the lowest price. The combination it remembered was what we chose for the final design. For draining water, the best combination was a flow rate of 19 meters cubed per second, a velocity of 10.75 meters per second, a Darcy friction factor of 0.03, and a turbine efficiency of 0.83. The code followed the same process for filling the reservoir, but the ratio was overall efficiency to cost. This way, the code could give us the best overall efficiency for the lowest price. The best combination for filling the reservoir was a flow rate of 61 meters cubed per second, a velocity of 34.52 meters per second, a Darcy friction factor of 0.05, and a pump efficiency of 0.8. By utilizing these two codes, our team determined the best combination of velocities, flow rates, pipe friction, pump, and turbine efficiency for both pumping and draining water. Here's the first code. At the top, we have all of the constants, and then we have all of the possible turbine efficiencies with their costs, the friction loss coefficients, and the possible velocity. This section of the code calculates all of the possible flow rates, velocities, and time values for filling the reservoir. The next section of the code calculates all the possible flow rates, velocities, and time values for draining the reservoir. So when we run the model, first it outputs all of the possible pumping values. So Q starts at 45, which would give the water a velocity of 25.46 meters per second and would take 4.91 hours. This continues as Q goes up by 1 each time until Q is equal to 79, and it has a possible velocity of 44.7 meters per second, and the time to fill would be 2.8 hours. Next, it prints out all of the possible draining values. Q starts at 19, and the velocity would be 10.75 meters per second, and the time would take 11.63 hours. This continues until Q is equal to 28, and the velocity is equal to 15.84 meters per second, and the time is equal to 7.89 hours. Next, we take these possible velocities and flow rates and put them into the second code. At the top, we have the same constants, and here is where the sets from the last code are put in. We use those sets along with the cost of everything to calculate how much final energy there will be from the system and the cost of each combination. And from there, it finds the ratio that is the greatest of final energy to cost and remembers the values at the biggest ratio. And then at the end of that section, it'll print all of those. And down here, it's finding the combination of velocity, pump efficiency, friction, and flow rate, and optimizing it to have the best efficiency for the lowest price. And it remembers the best possible combination and then prints it out. So when we run this, it gives us our final variables. So the final energy is 131.67 megawatts, and the cost is $17,410. And it only takes 11.6 hours to drain, which had to be under 12. And then for pumping, the energy in is 662 megawatt hours, and the cost is $24,969.
Our general results are the choice of Zone 3 as the building site of the hydroelectric system, using 2 pipes for greater efficiency, and having a reservoir 20 meters high. In addition, we have a raised pipe installation due to the variable slope of the hill that uses 2 45-degree bends. The diameter of these pipes is 1.5 meters. With regards to energy consumption, we are taking 662.97 megawatt hours in and giving 131.67 megawatt hours out over a fill time of 3.62 hours and a draining time of 11.63 hours. In the fill system, our pump efficiency is 80% and our Darcy friction factor is 0.05, while the flow rate is 61 meters cubed per second at a velocity of 34.52 meters per second. In the draining system, the turbine efficiency is 83% with a Darcy friction factor of 0.03, while the flow rate is 19 meters cubed per second at a velocity of 10.75 meters per second. The parameters determined by the model make up a hydro storage system that exceeds the client's needs of an output of 120 megawatt hours, as the system outputs 131.67 megawatt hours and drains at an optimized time of 11.63 hours. However, the overall efficiency of the system is about 20%. This is because the model had to consider cost effectiveness as well. Options that could have increased the overall efficiency were eliminated because of their cost. Examples of these include using better quality turbines and pumps, and pipe configurations that could lead to a more efficient system. The team anticipates that the total final cost of constructing the optimized pumped hydro storage system is about $1 million. In addition, our pumped hydro storage system stores 20% of the energy put into it, and without it, a significant amount of energy from the solar fields go to waste. Therefore, our system comprises an important step towards solving the problem of energy waste and efficient energy storage. Our system effectively optimizes the energy production of a system that uses solar fields to produce electrical energy to a community. Finally, this is a highly sophisticated model of a system that can evaluate various trade-offs of cost and power generation.